yeah, excited to build on Rust. It's actually our third time building the runtime, as you do in startups, and the first 2 times were in Go, and the third time's in Rust. So
great. How's it going this time around?
awesome.
Good to hear. Thank you.
Hi, everyone. My name's Andrew. I'm a roboticist. I've made it a shockingly long period of my career in Java and Python, given that I work in robotics. But a year and a half ago, I joined a startup called Scythe Robotics that builds autonomous lawnmowers and puts as much of it in Rust as they can. It's been fantastic. I love it. I'm having a great time.
Scythe, S-I-G-H-T?
Scythe, as in the tool that you...
Oh, S-C-Y-T-H-E.
Yeah.
Gotcha. We'll check them out. Thank you. Beautiful. Well, that's great. Every month we love to have people introduce themselves. What this does is lets us know like who's here, who's around us. We have members who have Rust in space right now. We have members who have, done things like submarine data centers and all kinds of interesting things. So we'll often find somebody who has a shared passion, and we encourage a lot of interaction with one another. I know we're stereotypically very introverted people, but it's also cool to meet one another and find people who have shared passions. Okay, so we have upcoming meetups, just to let you guys set your calendars. We typically meet on the 3rd Thursday of every month, unless there's some sort of major event like, oh, I don't know, Thanksgiving or something like that. So you'll see in November that we're meeting on the 2nd Thursday. We may move the December meeting because that's pretty late in the month and we could lose a lot of people already to, being on vacation. So we may move that up a week. I will speak to the folks here at the reactor to see if the 2nd Thursday in December is actually available. Would that work for everybody if we move that to the 12th, or would that present? Yeah, it's okay. Great. Okay. After this meeting, when the weather's nice, you'll find we generally have to leave fairly punctually at 8 o'clock in order to let our hosts get home and get to dinner. But often we gather right outside the front door there for even an hour. So it's a great way to meet somebody who talked about a topic that you might be interested in. On most days and some days when the weather is not so nice, as might be coming up in the winter, we also meet at the Flat Stick Pub, which is at the Redmond Town Center, not too far away, and get together and chat as well. All are invited to go there and meet up after. So a couple of announcements. For the last 2 meetings, we have been doing recordings and placing those recordings on YouTube. So as you can see, we're in a meet session right now that's being recorded. We'll be able to place this on YouTube. You'll always be able to see those at this URL. Yeah, please, if you missed a meeting, you'll always be able to check it out there. We also try to get different folks speaking. So if you have a topic that you think you might be interested in talking about, please let me know. We would love to have you come up and give a talk. A lot of beginners might say, well, I'm a beginner. I can't, lead a talk. And I would like to challenge that assumption. I think it's a terrific way to learn, to come up and say, here's something that I'm working on. Here's some of my code and I'm stuck. You've got a room full of people who are actually super engaged and would love to help. And when I've done some live coding and I'm in the moment trying to weave a narrative and I get stuck on something, I get all kinds of wonderful help from the group saying, oh, this is why it doesn't compile, or this is what's going on. So please don't feel you have to have all the answers. I've also modeled some presentations where I am presenting a video on YouTube that I thought was really interesting. I thought might be useful to the group. And I've tried to pick something between 10 and 20 minutes long. And then the video plays and I'll pause it at interesting points and we'll have a discussion about that. Or if I don't have the expertise to be able to lead a discussion on that, I'll pause it and ask questions about that. So you can be at any level of Rust. And if you think you have something, please reach out to me, particularly on our Discord channel, and I'd be happy to work with you to get that presentation wherever you feel it needs to be, and you'd be more than welcome to present it. Okay. So just by show of hands, does anybody have a topic or something that they think they might be interested in presenting here? Anything? Maybe? Okay. It's not a commitment that next month you're going to be presenting. It's just a question to see like who has something they're working on that they'd like to share or something that they want to talk about. Any thoughts? Anyone? No? Yeah, maybe. Okay. So there's a few topics that we could talk about. So please, if you're not on our Discord, I'll quickly jump back to that in case. Yeah, our Discord link, you can take a photograph of that. Please join on our Discord and then reach out to me and we can chat about your topic and figure out when, if, you'd like to schedule it and get you slotted in. We've been running a little experiment for maybe 3 meetings this year. Earlier this year, every other meeting, we did a hands-on embedded course lesson. And so what we did is we have these Raspberry Pi Picos, and everybody brings their laptop and a USB cable. Remember the USB cable because we run short. And then we plug in, and we did some bare metal Rust development. Blinked the LED, made a little interactive game, ran 7-segment LED panels and a few things like that. So I've had the request to continue that. And so the question is, can we go to the next step and actually teach how to do remote debugging? That's where your computer's in control of another CPU or microcontroller. And the answer is yes, of course we can do that. And I actually have the little debuggers that we can use to do that. So either October or November, I will present that, and I'll let you guys know ahead of time so that those who are interested can be sure to be here, and those who are not interested can be like, I might skip that one. But the intent is for anyone at any level to be able to do this. We're gonna blink an LED or do something only slightly more complicated, something very, very basic, the equivalent of hello world. But we're going to learn how to use debugging tools. And for any of you who have debugging experience in, say, like C or something like that, you're going to be shocked at the difference in the the difference in the quality of the debugging tools. So that's a little teaser for you. Who here went to RustConf in Montreal? See one. That's it. Who's here tonight? Okay. Would you like to share anything about the trip? Give us a little trip report. How was it? What did you see? What was interesting? Would you be interested? Okay. Well, let me give you the mic here. That's okay. Just whatever you saw, whatever you remember.
Uh-oh. I actually have very few things to report about talks. I'm looking forward to watching a bunch of them on YouTube because I ended up doing hallway conversations basically entirely of Thursday, for example. There's the Discord for the RustConf had some interesting notes from the space talk about a date time library that I'm curious to look up. I'll be interested to see how they do that. There was a neat talk about some ways of encoding nicer ways of writing parameters in a I forget what the backend was, some data store wrapper layer that was using some interesting tricks with builder methods and into future and like this to give a nice ergonomic API that still had a bunch of variety to it. Yeah, I don't really have much to say. Sorry.
That's fine. That's fine. Thank you. Thank you.
I don't think it was burnt sushis, but it might have been. I haven't seen the talk yet.
Thank you. All right. Sorry. Did I go? No, I did not go. I am very, very busy at $ day job. It's a startup, and we are hoping to launch this year. So it is crunch time for me, which is why debugging embedded projects says October or November. So that's what's going on right now. Last thing about announcements. Does anyone else have an announcement they'd like to make to the group? Anything Rust related you think the group would find interesting? People hiring, new products that you think, Rust related that we should check out, stuff like that. Any announcements? Nope. Quiet group tonight. Okay, sounds good. You found the same bug in 2 different WebAuthn libraries. You found the same bug in 2 different WebAuthn libraries today. Okay. Did you submit a PR? Okay, all right. Well, we trust you'll do that. Great. Yes. Let me get you to say that again because I won't be able to repeat all that.
We Spice AI are hiring. We're a VC-backed startup here in Seattle. We have space at the University of Washington CoMotion Lab Startup Hall, and database engines, data systems, ML, all written in Rust. And yeah, just always hiring smart people who want to work on cool stuff together. And then one more announcement is we are also hosting the Apache Data Fusion meetup in October, which will be the first time they have that in Seattle next month. And I'll post a link in the group. So if you're interested in data systems on Apache Fusion as well, in Rust, then come and hang out.
Very cool. Thank you. I'm just trying to avoid feedback from that speaker in my microphone. All right, so we have 2 talks tonight. First talk is Tailwag. Nick, you here? Yep, great. Come on up. Our first talk, intermediate level. We're trying to have something that is beginner level at every meeting, so that way there's a little something for everyone. So this first talk will be a Tailwag by Nick. You are the author, right, of this batteries included web framework in Rust. So this is great. Our second talk will be a follow-on to our intro to async by Jack shortly after. So do you want to present? Okay.
HDMI cable.
There is, but it won't work. You'll have to join the Wi-Fi.
Okay.
Can help you with that.
I don't have any kind of Aircaster stuff set up on here.
Okay, well, we'll try the HDMI. We'll see. The folks watching at home might not have as interesting a presentation to watch.
It's on this side.
Okay. Yeah, I think you know what we'll do. HDMI isn't going to help us. What I'm going to have you do is open your browser and go to that URL.
Okay. The Rust 9/19.
Yes.
Oh, next just Teams. I can that.
Yep. And
No
then
mic,
type
no
in any
camera.
name. Yep, no mic, no camera, and join. And then you should be able to share your screen, especially if I stop sharing mine. Right.
Erase this. Okay.
Yep.
There we go. Hello. Can you guys hear me?
My name is Nick Gilmore. I'm going to talk about TailWag, which is a library that I've written in my free time off and on over the last year or so. A little history about me. I studied computer science at Trinity University, and since then I've worked in many different industries. Excuse me. From banking to big tech to startup. And this is my dog's band, my dog rock band called the Ankle Biters. They are the inspiration for the name TailWag. And those of you that know me know that I love my dogs a little too much and talk about them a lot. But TailWag is named after them. And the idea was to be the batteries included framework that I found a lot of forum posts asking about when I was looking for it. It's experimental right now, but it works for some use cases. And the goal when I set out to do it was I wanted to be able to write just a basic struct and get a CRUD API out of that, get the database stuff for free, get the basic REST API for free, and have a web portal where you can just go and manage your data. Just simple CRUD stuff that you really have to glue a lot of pieces together for when using the existing web solutions, because you can get the stuff for the API, you can get the stuff for the ORM, but you still have to glue a lot of it together. And then authentication and authorization is something I've got some basic stuff implemented. It hasn't been fully tested. And the idea of just the database magic. If I've defined my struct and I want everything to come from that. And I'll talk about this a little more, but when I talk about magic, the core API or the core macro for it is just called magic. And if you look at like stage magic, a lot of it is what you see is something appearing out of nowhere and disappearing. And what's actually happening is the magician is doing a lot of work to hide from you all of the tricks and all of the engineering involved in doing that. And so when I talk about magic, that's what this is there's a lot of stuff happening behind the scenes, but the idea of magic is you don't need to worry about it. You don't need to see it. You just get to write the code you want to write. And so a lot of the patterns that I used relies heavily on derived macros, and I specifically focused on derived macros because I've used some macros that write so much code that I don't even know what they're doing behind the scenes. And this does a lot of that as well, but you can go in and override and write custom behavior with derived macros, whereas proc macros are just other code and it can do just about anything. I used a manager pattern where I generate some data managers for the structs for those types. And there's a lot of stuff that goes on behind the scenes, a lot of different types to make that work together. The extension pattern is one of my favorites where you can add function calls and methods to other types. I use it a lot for string. I can show later like a two snake case and stuff like that, where you define the trait and then you implement the trait for the specific type you want. And now that type has all the methods you wanted to add to it. Builder pattern I relied heavily on. And then this thing I called generically generic, which uses std any. And I ran into this problem where I was using generics, and when you have generics, every type for that generic type is its own type. I said that a lot. And that ran into some issues when I wanted to be able to like get an instance of something related to a particular type. And I can show this later when I get to the code, but after I'd solved some of these problems, I was like, how do those other web frameworks do it? And I went to look and see how Actix Web did it. And we ended up doing it pretty much the same way, as far as how you turn any function with arbitrary number of arguments into a trait or define a trait over a function generically. And I'll show that because it's hard to talk about without the code. So what I wanted to do here was give a quick demo of what this framework does. I'll walk through just writing a quick to-do service, and I'll show you the React application I've written to generate that web management portal. I'll walk through some of the crates and how they work together. And then I'll show you one of my favorite things that I really liked how it turned out of being able to filter things in the ORM using a iterator-like syntax. Can you guys still hear me if I'm over here? Or do I need to drag this? So let's go. Here we go. here is the to-do demo right now. It's just a hello world. And I've pre-added some dependencies. I've got chrono for time, serde for serialization, SQLX for the database SQL execution, and tailwag is the library under the hood, toke.io for the async runtime, and UUID. One of the limitations that it has right now is every type has to have an ID with a UUID. I just built a lot around that. But the idea here was to be able to define a struct. So we'll say, we'll just call it a to-do struct. We give it an ID. We can give it a description, or let's say a title as a string, and a Boolean for completed. Yeah, we can start with that. And all you have to do with tailwag is use this derive magic macro and wrap your struct in it. And I'm actually not going to do derive magic. I'm going to use the prelude because there's going to be a few other things in here. And it wants braces, not parentheses. That'll get me every time. And this generates all of the traits needed to build our API. And if you want to know what's happening behind the scenes in this derive magic, if we inline it, it's just a whole bunch of derive macros. We've got some standard ones: clone, debug, default. We've got some serde and SQLX, and then all of these. The get table definition is the one. It generates a schema definition that's used to create the create tables and all of that, and that's fed into a type I've created called Postgres Data Manager that will manage the insert, update, delete queries for that. These three don't. They just kind of all work together with that database management. The filterable piece here, that's how you can, like I said, use iterator like syntax to filter your data, and it actually builds the SQL query dynamically as you do that. And then this build routes generates the actual web API piece of it. And then this get form exports a JSON schema for a React library that I wrote a couple years back called Formiliar, and that's what we're going to use to generate our forms. But for now, we'll just call it magic. And then we need to write our main function. So we'll start with a web service. We'll give it a name, to-do service. And we will add our resource to it. And that type is our to-do type. And then from that, we will build the service. We'll run it. And we'll await it and unwrap the result for the sake of the demo. And this is our entire application right here. So if I run this, then I get compile errors. All right, not expected. Because I don't know how that got in my cargo toml. Let's try that again. It's still red, but I think that's just a compiler or a delay. Got some big warnings. A lot of the security of it hasn't been tested. Would not recommend using it in production right now, unless you're willing to live on the edge. And it's hanging right now because there's no Postgres instance to connect to. So I'm going to come here, and here this is just going to start up a brand new Postgres instance. We've got our default Postgres username and passwords. And so now let's try running this again. And it'll run, and it's connected, and our API is up and ready. And then the other piece here is this React application that I'll start. And what that's doing, actually, I have to copy this JSON file over first. One of the outputs of the build is this JSON schema here. If you look at it, it just defines, excuse me. It just defines the forms needed for the field. A lot of this is just piped directly into the HTML. I'm going to go ahead and copy this file to do.json and paste that here into our managed form. And here, that's very small. But we're going to put it here. I've got a demo to do from my dry run. We're going to paste that file right there. And if we then run our NPM application for the front end, that's just taking that schema and it's going to build this form for us. We can ignore the ID for now. Yeah. Which one? What is hanging over it? Did I get it? Yeah, I don't see that on my screen. Oh no. Can I move the window? Will that help? All right, and I'll zoom that in a little, and you'll see it's got this. It just pops up a form. We'll give it a title, test to do, and it right now it's not refreshing automatically, so I have to manually refresh to do number 2, and we'll mark that as completed. I did it twice by accident again. These delete links work. You can edit one. I'm going to give one with a different name to show something else later on. New task, not a to-do. I'll mark that as completed as well. Doesn't really matter that much. But that's just hitting that API that we wrote with like 15 or so lines of code. And so what's happening behind the scenes there? Well, we've got this with resource here is going to take that to-do that derives all of those traits. And it's going to add, I can pick this up now. It's going to add the data definition or the table definition that's derived from that get table definition trait. It's going to add that to a registry associated with a type using the type ID. Sorry, this isn't, my hot links aren't working moving around the IDE, but it's using those traits to just generate schemas and pipe those through in a generic way. And it's there. I ran into a lot of issues trying to do what I have a lot of issues with how wishy-washy Python is with things sometimes. But I was trying to do some things like that where I can just make assumptions about the data structure, and you can't do that in Rust, as I'm sure many of you know. So I had to find a lot of creative ways around that. And I've got a bunch of crates over here that come together to make it. I learned a lot about writing derived macros. I made a lot of things way more complicated than they needed to be early on. But the core crates here, there's the application which handles all the web HTTP piece of it. I started out building this on top of Axum, and then I hit some issues with the type checking where Axum wasn't quite compatible with the way that I built my thing. So I ended up just implementing the HTTP spec there. This GUI crate uses eGUI under the hood to basically do the same thing as we saw in that React application. The forms generates that JSON schema. This open API generator doesn't do anything yet. And then the ORM handles all of the database stuff. The last thing I want to show, and I can show it here actually, because this is, again, my dry run here, but this filtering. So we write this function here, and this function here, filter to-dos, we take in the path string, and we take in our data provider. And this right here, all of the behind the scenes magic is going to convert this filter to-dos function into an HTTP endpoint. And that was where a lot of the difficulty came of trying to generically implement a trait over an arbitrary number of functions. So that's the piece I want to close on, I think, and show. Yeah. Yeah, it's creating all your CRUD endpoints. It's got Git, it's got list Git and detail Git. If you pass it in by ID, it's got your post to create, patch for updating, and delete. And it's just giving all of those for that struct. And right now it supports flat data structures and one-to-one relationships. And I'm halfway through getting one-to-many, and then many-to-many is something I haven't thought too much about, but yeah, I can actually, I'll show an example of that because that was this filter piece I wanted to demonstrate. Yes, we are on the thing. So the question was, the first question was, is it giving me that code that I wrote, giving me all of the HTTP CRUD endpoints? And it is. It's giving me that post, patch, delete, get, all those CRUD endpoints. And then the other question was, how do you do searching, right? How do you search through the data and filter the data? Is that yeah. So to do that, I've got this filter API. And so if I come to, let me make sure I'm in my right window because I've got way too many workspaces up now. But if we come here and this is our to do, so I'm going to write a function here and it's going to be an async function. I'll make it simple. I'll say filter. We'll give it a title filter, which is going to be that path string. And path string is just, there's some extractors in there that will extract a string from the path variables in the URL in that path that you get. And then the other thing I need is the data provider. So we'll pass it that Postgres data provider. And we want it to return a vector of our to-do object. And so we come in here and we go to-dos, which is our Postgres provider, and we want to search with a filter. And the way I've implemented this with filter is one of the things that those crazy derive macros gives you is it generates filter types for the individual structs that you have. And what that does is it goes through and anything that is a filterable type, it creates a bunch of builder methods for you that you can string together filters. So this with filter, we'll pass it in a closure that takes in the to-do that we're filtering for. And so if we want completed, we can say we want to filter where to-dos are completed. A lot to do there, so the compiler's happy. And I've overridden the bitwise or bitwise and operators too. So if you want to chain things together here, you can and them together. So we want completed things where to-do.title is like, and this is using our Postgres like strings. So we want it where it has the word to do in the title. And I'm going to go back to my thing here, make sure I had the case right. And then so back here. So we've got that, and that is our query. And if you look, that query type is an executable query on the type to do. So that is, it's got a bunch of metadata in it that will generate an SQL query at runtime. And so to run it, we'll say query.execute, and then we await and unwrap to avoid for any errors. And that actually gives us our vec. So if we do that, you can see that is executing to a vec of to-dos, and then we'll return it at the end. And so to add this endpoint, which I called filter, we can annotate the to-do. And this is one of the derive macros, looks for these annotations. And we will say it's a view. I called them views. The inspiration for this was working with Django at my last job. Django does a lot of things for you, and it also does a lot of things to you. I get from the laughter that some of you know what I'm talking about. But you know, I hijacked this views terminology from them, and we're going to give it a name. I'll just say slash filter, sorry, endpoint. And this name doesn't matter at all, but the curly braces to indicate that it's a dynamic variable. And then the function that we're passing in is filter. And you'll see I wrapped it, excuse me, in inside of a tuple. And that's just because of the way the views work is if we want to add a bunch of views, we give them all the sets of those. And so we can add multiple functions there inside that views attribute. So this generates a filter endpoint with that takes a path variable that is then passed in here as the title. And here I put the word to do, but what I wanted to do actually is to call it that filter or title to actually pass in that variable. So we can format that. And something else that I'm going to have to do here. Yeah, it doesn't like that. That's a path string, so I can come here and say let title equals reference of dereference of title. And that takes it from that path string to a string reference and makes our compiler happy here. So now let's restart this service. Gotta kill the old instance and run it again. Sorry, I'm working on a much smaller screen space zoomed in than I'm used to at home. So things are just jumping around. But if we run that, then we can, let's open it up in a browser and go localhost 8081 / to-do / filter / our string, and it gives us all completed to-dos that have to do in the title. What's that? Thank you. Yeah, he said that's slick, and I thank you. I appreciate that. Yeah, so that's Tailwag. It's on GitHub. I just pushed an update to crates.io today. I don't publish the crates too often because it's not quite stable enough for me to care too much. But if you are interested, go star the GitHub page. You can pull it down there and try it out. I think I've used up plenty of time now, but thank you so much and hope you enjoy. I'll go ahead and get back to the slideshow real quick, actually, just to talk about, I do have one last bit, which is the current limitation. So it supports flat data structures and those one-to-one relationships. It does have some support for queuing tasks up. I've used this to write a basic shop that connects to the Stripe API. So it'll queue up those events from Stripe to be processed. It supports static files if you just want to serve those and those customer routes as we showed. It has port support, has some very basic authentication authorization rules. I'm working right now. Right now, it only handles one request at a time, and that's because I ran into some issues carrying sync and send through everything. Those are contagious traits. I'm working on migrations. The code is written to migrate from version A to version B, but I haven't integrated it yet. One-to-many and many-to-many are on the roadmap. They're in progress. And then I've got some dependency upgrades to do. Like when I was putting this demo together, SQLX just throwing a bunch of errors because they've updated. I think they had a security flaw that they fixed in 0.8. Yeah, so if you have any questions, reach out. I'll put this slide up as well. I'll post it in the Discord after this. There's my email, my GitHub. Reach out about this if you're interested in my dogs or my music. Or one thing that I just got through a big round of interviews. And if anyone needs help with interview prep, please reach out. I just love to talk about that stuff. Thank you.
Thank you, Nick. All right, so let's take a 10-minute break before our next talk. I saw. I'll take care of that in just a moment. Nick has the URL stuck to his computer. It's on a little post-it note. Thank you.
Good.
Yeah, we just have a couple of folks asking about the live stream URL, which I neglected to publish. So I'll put that online while we take our little break. Yeah, I think so. What was that? The 5? The 5? Raspberry Pi 5? The Pico 2. I have not tested it out. They put another, should I put this on me? They put another micro USB port on that thing, and I'm just so upset. I'm boycotting just because of that micro USB. I'm publishing that to the Discord as we speak. You will join this URL
Okay, okay.
and you will
Okay.
here, I'll give you this. Well, I need the post-it note as well to
Can I steal your lapel mic too?
yeah, I can get you another one right over there. Mhm.
I'll go and come back.
Okay.
Let's get this. Let's get this.
So much communication.
working. Yeah, before it's bad.
Discord.
Yeah. Okay. No camera. Yep. Sure.
All right. So
Okay. It's Rest 9/118. Yeah. With Chrome on Linux, it's gonna be able to figure this out.
we'll see.
Allow this to. Turn off my my microphone. Yeah, I do plan to make it.
AKA MS.
Are you remote? Zoom, I can click share here.
Yes. And you'll take over the screen when you do that.
Are there anybody else? That's one. And his name was Andrew too. So there were two Andrews from Seattle. But you're not. It's me. Yeah. You've been there for a year and a half. Yeah. Same memories. Yeah. Other people.
Okay, so for those of us who are online, we should get started in maybe 3 or 4 minutes.
API.
Let's see. Okay, so let's bring everybody back. We can get started. You have your mic. Looks like you're ready to go. Yeah, as long as it's off. It is off. Yep. So it will not pick you up in stereo.
My green light is now on. I hear a little bit of whine.
You're good.
Okay. Okay.
Yeah. If you stay away from that speaker, you will not get feedback.
There is a monitor pointed directly at me.
Yes, there is.
I'll do that.
Here, I'll move it for you.
All right. So I have on the screen the URL to the page that is open behind the URL, which is a draft post of a series of blog posts I'm putting together now. And I'm going to mostly just read from it. I'm not going to read from it. That would be terrible. I'm going to use it because there's a bunch of code examples in there. And I'm going to pop them up on the playground and we're going to run. So anybody who wants to pull up this URL, you should be able to find all the same playground links I'm going to click on. You can run the code as we go. Part of my goal here is for this whole thing to be based on examples of running code that actually like work, and you can play with them and you can put print statements in them and all that. So we just listened to Nick's talk. That was cool. And if you are one of the 60% of us who are beginners, no doubt a number of mysteries sort of came into your ears and maybe came out the other side. And one of them was like procedural macros, which I'm not going to talk about at all. That's going to remain a mystery. We're not going to talk about that. I'm not sure I could even answer any questions about that one. But another potential mystery that might have floated into your ears was the Tokyo runtime or the Talk.io runtime. And we're basically going to talk about what that means. Like, what is a runtime? What is async? What is all this stuff? That's what we're going to talk about. It is very hard to give a short answer to that question. So mostly we're going to be sort of beginning to explore a topic that sort of eventually answers the question of like, what is Tokyo? I gave the first 10 minutes or so of this talk last month. 10 minutes is not very much and half of us weren't here anyway. So of course, I'm just going to start from the beginning. The way this is structured, there's sort of like intro, which is like the 10 minutes. And then there's 3 parts. And my goal is to do part 1 today. And then, part 3 isn't even written. So that's, we're not going to get any farther than that anyway. I think eventually I want to try to like record this and sort of have a video to go with the article. We'll see how it goes. But we're just going to look at part 1, futures. That's our goal right now. So here we go. Raise your hand just so I can get a sense. Raise your hand if you have not written any Rust yet. Cool. I see at least 2 hands. Raise your hand if you have never used threads in any language. Hands. And raise your hand if you've never used threads in Rust. Several more hands. Cool. So threads, I think most of us, but not all of us, know that threads are a way to get our programs to do more than one thing at a time. Async is also a way to get our programs to do more than one thing at a time. And we're going to be talking about the differences between those things. But the way I like to start is by talking about why we might not want to use threads for everything. So I'll scroll down to our first example. Don't bother to read any of this stuff. Too much anyway. But we're going to look at this little multi-threaded program and run it and talk about what it's doing and then break it. And that's kind of how we'll get started about what async is and why we might want to learn about it. The function that we're going to use in this program, foo, this is our basic like little unit of work. Let's get it in our heads what this does. We're going to print something. We're going to sleep for a second as though we were doing some work or something. And then we're going to print something again at the end. And so if we wanted to run foo 10 times, that would take 10 seconds and that would be annoying. And so here's an example of using threads to run 10 foos at the same time. So this should take 1 second to print 10 pairs of messages. Last month, Brad, ran us through a lot of examples of threads. A lot of us saw some of these basics before. I'll show it real quick. So this, I have clicked this playground button, and that should open the example in the playground. And that's too small for anyone to read. So I'll do a lot of zooming in and out, but that's the same code that we just saw. And if I run it, prints the start messages, prints the end messages, and we can all agree that was like approximately a second or so. So that just ran. And so for the folks seeing this for the first time, foo is the function we wanted to run. This vertical bar syntax here, who's seeing that for the first time? 2 vertical bars. This is how Rust writes lambda if you're coming from Python. These are closures if you're coming from C++. This is like a function. Foo is a function, but this is the function that calls foo with a specific argument n, which it is capturing from the environment here. The move keyword has to do with a lifetime error, which we're not going to dive into. If you have not yet fought with the borrow checker, that will be a different talk. But this forces the closure to copy n. And then thread spawn takes this closure. I don't know if I just said this or not, but the vertical bars are like the parentheses of the closure. So this closure has no arguments. And it does this one line of code. And thread spawn says, I will call you, the closure, on this new thread that I spawned, and it will run in the background. And so this loop calls thread spawn 10 times. And those 10 calls to foo all kind of get kicked off. Yes.
Not too much to the borrow checker, I would go with that. But the thing that came to mind for me was if n was something non-trivial and you're copying it every single time you pass it to a thread, that could be a huge amount of overhead work. Is there a way to not do it without a copy?
Yes. So the question is, to paraphrase, should we worry about n being copied here? It could potentially be a lot of work if n was like a bigger thing than an integer. I think n here is probably going to default to a 32-bit integer, but it could be something bigger. We could worry about that. I think it's actually interesting that in this case, the fact that n is copy, which is what Rust calls these things that you can copy any number of times, the fact that n is copy is actually our problem here, because if n was not copy, so foo takes n by value, right? And if n was not copy, that would imply, Rust would figure out that means that this closure must take ownership of n. But because n is copy, the closure is going to be like, oh, I don't need to own n. I can just copy it every time I use it, except now I have a reference to it. So it is unfortunate that n is copy here. And if n was not copy, it would be moved into the closure and never copied.
Then if it's owned by one of these threads, you create 10 of them, would that create issues with like 10 different threads? Like take
Right.
From it, certain threads, or if it's copy type, it's supposed to cheat. The fact that it's our move there is that it would never make expensive copy, or what's called a flow. You got moving stuff.
I'm going to cut off this tangent because answering performance questions requires having a specific example of a performance problem sort of in front of us, and we don't have that, so we're all kind of imagining different things. But let's absolutely circle back to that and talk about it at the end, or when we all get pizza or something like that. So we're spawning these 10 threads. They run in the background. I didn't split it out into lines. We can see that spawn returns something, which is then being pushed into this vector of thread handles, which suggests that what it's returning is a thread handle. And then at the end, we loop over all those thread handles and we join them. And join, as I know most people already know this, and this is a review for a lot of people, but it's good to review. Join means wait for the thread. So it's actually a little bit counterintuitive. So of course, again, a lot of us have seen this before and don't even think about it. But this loop is going to spend almost all of its time on the first call to join, right? It's going to wait for the first thread, and that's going to take a second. And then the loop's going to continue, and all the waits for all the other threads, since they all ran at the same time and all pretty much finished at the same time, those joins should return pretty much instantly. We don't really care which one we join first. We're just waiting for them all to be done. So that's threads, which a lot of people have seen a lot of before. And this is running 10 things at the same time. Cool. So, sometimes we get on the web like Nick and we write our multi-threaded web servers, and then we start trying to scale them. And instead of having like 10 requests or whatever, we have like 10,000 or something like that. And we start to find that these threads aren't great. They don't work great when you have so many of them. So here's a quick example. I changed 10 to 100 here. I could just edit it in line. I think I probably will. So doing it 100 times, it actually works fine. You can see, you can see the order is kind of, maybe a little bit random. That's one of those things that happens with threads. And there's all the end threads, and I don't know, it was probably about a second, right? So 100 works. But if I bump this up to 1,000, has anybody tried this on their own machine? Like, how many threads can I spawn before I crash? If I try to spawn 1,000 threads on the playground, it panics with failed to spawn thread. Zoom in, yes. You want more of the code or the error? All. The problem is that they're gonna like get truncated, but yeah. So if we try to spawn 1,000 threads at the same time, it's just gonna crash. When I do this on my own laptop, I can get up to about 19,000. I think my, it's sort of, your machine probably has looser limits than the playground, but the playground's limit is somewhere around 1,000. Threads take a lot of memory for various reasons. There's overhead associated with spawning threads, and that's no problem when there's 10 of them, but when there's like 10,000, it's a problem. Let me know if I need to change anything, or happy to play. So, right, so that's not great. We could also, folks who work with a lot of web servers probably know that even if you can spawn 10,000 threads, which you sometimes can, the performance is not great. We sort of hear about this. All this thread context switching is expensive. It is surprisingly difficult to produce a good playground example that demonstrates that fact. I have one, but it's a bad playground example because it's like 100 lines. It's like you could try to pass basketballs back and forth through channels, and we could just take it on faith that these threads get expensive. But I think it's fun to just notice that we can't even run that many because we will just crash. So how do modern web servers, these things like Tokyo, how do they solve this problem? And the answer is async, and that's why we're here. So there's this other way of doing things called async code. And really all the rest of what we're going to be talking about is trying to build up some intuition for what it's doing and how it works on the inside and what makes it different. I can say it's sort of at a very high level, just to start out, when we spawn multiple threads, we're asking the operating system to do that for us, I suppose. That spawning a thread is a thing the operating system does for us. And then the hardware, hopefully we have multiple cores, and so our threads are actually running on all these cores. So it's the operating system and the hardware are doing stuff for us. That's kind of what threads do. And async is sort of instead, it also does a little bit of that, it can, but setting that aside, what async is going to do is it's more like we're going to reorganize our own code to do many things at the same time. And that's a very abstract way of putting it. And if you haven't seen the guts of this, that doesn't make any sense. Like, what do you mean reorganize our own code? And that's kind of what we're doing here, is trying to put some examples on the screen to make that make sense. But that's what async is going to do. So I've just thrown some code on the screen. We're going to look at our async foo, and we're going to look at some little Tokyo examples that call foo. And they're not going to make any sense at first. And I just want to look at them and run them. So async foo, async function foo. OK, so I guess it's different. Async, whatever that means. Printing, nothing's different about printing. And we see, OK, instead of, let's go back. What did foo used to do? Foo used to thread sleep. That's standard thread sleep. Now foo is going to Tokyo time sleep. OK, it's a different function, same duration. And then when we do that, we await it. So, OK, so like async functions await things, but it still looks mostly the same, whatever. And here's a quick example. We see a proc macro here, which I'm just not going to talk about at all. This is just the thing you put in front of your main function when you're using Tokyo. But this is the simplest possible example of calling an async function 3 times. So, OK, again, we see that we just kind of paste await there. OK. We're just getting that visual in our heads. And we can run this, and I'll try to make the size legible if I can. So if we run it, it should go start in 1, start in 2, start in 3. I kind of had to scroll to do that. Let's zoom out just a little bit and run it again. So, OK, so that's what async code looks like. That doesn't really tell us much about what it's doing. Any questions so far? Yeah. Yeah, good point. Good point. I had said I was going to do things at the same time, and I'm clearly not doing that. This is 1, 2, 3. So good point. Let's scroll right down to this example, where instead of doing those 3 things back to back, like foo, 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 we're going to do them at the same time. And let's just run it to keep me honest. So not even having read the code very carefully yet, just running it. Zoom out a bit because again, it's yeah, there it was. It was starting 10 starts and 10 ends. Okay, so that appears to work. And then let's look at it back here. So, okay, so I've still got a vector and I'm still pushing stuff into it, but instead of calling those things thread handles, I'm calling them futures. Okay. And we'll see that one thing to notice, I'm not, so previously I said foo await, and here I'm not saying that. So I guess if you don't await the async function, it like returns something, which I'm calling a future. Okay. And then instead of looping over the vector and joining the handles, we're doing some other thing. We're joining the futures into a single, bigger future, which I'm calling joined future, whatever that does. And I think actually one of the most interesting parts of what's coming is going to be the part where we rewrite this. We write this ourselves and see what this is doing. But for now, it is pure magic, and it's returning some future. And now finally we await that one thing. Okay, so whatever that is doing, that is achieving 10 things at the same time. I realize that it's not much of an explanation, but this is just kind of creating a hole that an explanation can fill. Okay, question? Yeah, so the question was, we'll see if I can even answer that question. The question was, now that we're using futures, why does it always go in order? And yes, that is an interesting observation, and it's not random. So if I run it, we'll always see it going 1 to 10 every time. I have to be careful with the answer because sometimes that is not what it will do. We will, when we get to tasks, which we probably won't today, we'll see it not go in order, which is funny. I think what I want to do, if you'll forgive me, is let that question sit in our minds. Why did this go in the same order every time? Because when we write the code ourselves, it will become incredibly obvious why it did. And until we do that, it's just we don't have the right hole for the answer to fit in. I think it's the right way to put it. It's a great question. It did go in order. So I guess part of what we're seeing is these things must not be running on a bunch of different threads, because if they were running on a bunch of different threads, we definitely wouldn't get this consistent ordering. So that's a good, that's part of an answer, right? So whatever's happening here, it is not running those 10 things on different threads. Oh, hey, wait a minute, really? Yeah. See, this is why I said I had to be careful. Really? Am I surprised by that? That is funny. Yeah, that's probably like Tokyo sleep scheduler magic. Like the answer is I actually don't know. Fun, great, love it when that happens in front of an audience. They started in a predictable order. Fair enough. Very funny. Okay, maybe the answer will not be obvious when we get to the end. I'll cop out of that one. So before we start, so my goal here is going to be to take all these mysteries that we've seen on the screen. I probably should have opened with this, but I count, there's 4 big mysteries here, and one of them is the macro, and we're just not going to talk about it. But there's 3 mysteries that we see and we do want to talk about. So we see, for example, we have this, let me scroll back up, we have async function foo, and I would like to know what that means, what that does. We have join all. I'd like to know what that does. And we have this Tokyo sleep, which is somehow different from regular sleep. So those are the 3 kind of magic ingredients that have appeared on the screen. And I would like to translate all of those things into regular, non-async, not magic Rust that we can actually understand. So that's going to be my goal for the rest of our time, next half hour or so, is to translate those things. And that will answer some questions, maybe not all. Did I see any other hands? So that's what we're going to do. Before we dive right into that, I want to make what I call a couple of important mistakes. So we can learn a few more things. We can get a little bit more intuition by taking that example and screwing it up in a couple of interesting ways. So here's one. So what have I done here? I took async function foo, but I put the old sleep back in there. Right, so that's the sleep that blocks a thread, if that means anything to you. And here is that on the playground. So we can see in this complete example, the print is hinting what's going to happen. We're still spawning 10 of them. We're still doing that async join thing, but they have the wrong sleep inside of them. And if I zoom out and run it, we'll see what that does. So we thought we were doing 10 things at the same time, but evidently we are not doing 10 things at the same time. So something about that old sleep, that thread blocking sleep, has ruined our parallelism or made everything run sequentially or something of this nature. This is hinting at what we hinted at before, which is that I guess these things are all running on one thread, because if we block that thread, then that's going to happen 10 times and we're going to wait 10 seconds, something like that. That's an interesting thing to notice. This is also a very, unfortunately, easy mistake to make when you actually write async code. You do have to remember to not do this. That can be bad for performance. In this case, our performance suffers by a factor of 10. That's one mistake we can make. Another mistake we can make, and this will be the last one before we start diving into the work of rewriting this is our main function. And instead of, let me go back, what was the correct thing to do? Instead of using futures join all and awaiting the joined future, again, whatever that meant, instead of that, in this broken version, I've written something much closer to what the threads version was doing. So I might imagine that each of these calls to async function foo has kicked off work in the background. And I might imagine that I could do the exact same thing I did with threads, where I could just join them in a loop and they're all running at the same time. And what I will find, this is the same code. For those of you who know what pin is, this is an interesting observation. I will not go into it. But this is the same code. And if I run it, we will see that it does not work like threads do. So once again, sorry for all the zooming in and out, but once again, I have somehow sabotaged the parallelism that I was going for here. So evidently, calling foo and collecting its future does not like start the work in the background. That is not how it works. And it looks like we could put some more prints in and play with it. In fact, I encourage you to do that if you have time and interest. But it looks like that the awaiting, the thing where you wait for the future, is where the work actually happens. Because as soon as we put that in a loop and do them back to back, the work becomes back to back. Kind of funny. So there's a couple mistakes that are just kind of like hinting, gesturing at the reality of what's going on in the background here, which is that we're doing all these things on one thread, and we have kind of invisibly reorganized our code somehow. Or maybe I should say async has reorganized our code to do all these things on one thread. Any questions about that as we move to part one? That was the introduction, part one. So the first mystery that I want to rewrite in normal code is foo. So foo is our simplest friend here. It's just a couple prints in a sleep, and we're not going to look inside the sleep. We're just going to do it. So I'm pretty much just going to throw a bunch of code at you, and we're just going to stare at it. And I apologize in advance for that. This is sort of the only way I know how to do this, is to just put a bunch of code on the screen and then slowly look at all of it. I chopped it into a couple pieces. So this is what foo looks like as a regular function. So there's no more async keyword here. But what we're going to see, let me hop ahead to the playground and see the full example. What we're going to see, I know this is too small. What we're going to see is that main is doing exactly what we were doing before. We're still calling foo. Foo is still returning a future. We're still joining them. But we are replacing async function foo with a regular function. In fact, I guess I'll just keep this view up. That's probably a little bit better. So foo is now a regular function, but it is doing the same thing. I have not changed the caller. And it is returning something which we conventionally call like the same thing with a capital letter. It's sort of like how like iterator combinators like map or filter return like capital M map, capital F filter if you look at the Rust docs. So we're returning a foo, which I've written above. We're about to scroll to it. And okay, constructing foo does very little. We do call sleep here, but we'll scroll and notice we do not await the sleep here. So I guess we're getting that sleep future. We said that async functions, when we don't await them, return a future. And we're doing something to it. Hold that thought. going to mostly ignore that for a second. We'll come back to it. But we're just kind of storing the sleep future in a struct. We're storing the number in a struct, and I'm giving myself a bool. We'll see why in a moment. Here's the struct. No surprise there. We just constructed it. So it's got the integer in it. I think actually previously it defaulted to I32, and now it's going to be a U64. We don't care, right? And it's got a bool in it. OK. And it's holding on to the sleep future. And we're seeing something called pin. And I have to talk about it. And I apologize for that. And what I'm going to do is just lie to all of you, like really badly. I'm going to tell a very bad lie. And that bad lie is that pin doesn't actually do anything. And in the examples we're looking at here, that is pretty close to true. So in the examples we're about to look at, you're going to see pin, and you can close your eyes until it goes away because it doesn't actually change anything that the code is doing. And if we have time at the end, I will look at an example where that is not the case and where what pin is doing is important. But for our purposes, I'm going to try to ignore it. Is that fair? Can we all agree to commit this crime together? And we can see, by the way, I'm also going to ignore box. So raise your hand if you have not seen box in Rust before. We don't actually use it that often, I would say, especially in beginner examples. Sounds like everybody's seen it. It puts something on the heap. I'm going to mostly ignore it because we can usually treat things in a box like the thing itself. I'm going to do that. And we can see that, OK, that's the capital S sleep. So yeah, that by convention, that's referring to the future that lowercase s sleep returns. Fine. OK, but like, why does all this work? And the answer to why all this works is this right here. Is impl trait for type new to anybody in the room? I think everybody's seen that. So we are implementing the future trait for foo. So this is where all of the magic happens. That trait has an output type, and it has one method called poll. And let's see, do we want to look at the signature first, or do we want to look at the body first? Let's do neither of those things. Let's think, no, let's look at the return type. That is interesting. So poll returns poll. Gosh, you know, more of this, right? It's like what, like every lowercase thing returns an uppercase thing. Let me just pull up the docs there. Probably the easiest way to do this. So we can see that poll, uppercase poll, is a very simple enum. It's actually pretty much an option. I think they may even have discussed making it be option at one point in the design phase. And then I think they decided not to do that because the sort of the rules for how you use it are going to be very different. But as a type, it's basically option T. And so poll can be either ready, in which case you have a T, or pending, in which case you don't, which is sort of like option none. And this is related to, you know, why are features called future? You may have seen similar features in other languages where they're called that because the idea is you're going to have some value in the future. They represent this value that you will at some point get. And that's the idea when we say the value is ready. The future has provided the value that it promised. Sometimes we call them promises that it promised it would give you. That's what ready is saying, and here's the value. So OK, so poll can either say I'm done or I'm not yet done. Let's go back to the code. Right, so we're returning a poll, and our T in this case is empty parentheses. That's the unit type, the empty tuple, right? Because foo returns nothing, right? Functions that have no return type in Rust technically do have a return type, and it's this little parentheses thing. Folks might not have seen that explicitly, but that's how it works. You can write return paren after a function that returns nothing, and that will compile. So we're returning a poll of nothing. OK, so poll, the lowercase poll, gosh. Lowercase poll's first job is to return either ready or pending. So OK, so if foo is done, well then poll had better return ready. And if foo is not done, then it should return pending. So we can see that's the first sort of detail of the contract here. The other thing we can notice is that inside of poll, like there's the printing, right? So the work of foo has kind of gone into this poll function. It happens in here. So we can kind of see, we can already see that poll has two jobs. I'm actually going to say that poll has three jobs, and it's going to be a minute before we see the third one. But we can see two of the jobs. The first one was returning that poll type, right, ready or pending, and the other is doing the work of the function, right, doing foo's work, which in this case is printing. So we can see that we created it, and when we created it, we said that started was false because it has not started. And we can see, okay, the first time we call poll, that's going to be started is going to be false. So this condition is going to be true. So we will print, and then we'll set that to true. Okay, so the first time we call poll, it'll print the start message. And then what will it do? It will call poll. Gosh, there's so much machinery on the screen at once. It will call poll on the sleep future. So I guess I should highlight that there are a couple things that I'm just going to squint my eyes at and ignore, which is a terrible sin of me as a teacher. But so this context thing is here. We can see it getting passed in. I'm not going to look at it. We'll come back to that in 2 examples in the future. So context is getting passed along. Okay. As mute is converting from a pin box, which is what we saw, the sleep future is a pin box. That's converting from a pin box to one of these, a pin ref mute. And we're ignoring pin. So that's just converting from a box to a ref mute. Okay. So it's not very interesting. In this case, it's a ref mute of the sleep future. So this is just taking a mutable reference to the sleep future and calling poll on it, which, as we know, is asking, hey, sleep future, are you ready? Right? And of course, in the case of the sleep future, ready is going to mean it has, done the sleeping, right? The time has passed. That's what makes it ready. And we can imagine that the first time we call sleep future poll, the answer is going to be no, because that's going to be like, we just created the thing, right? So a second has not passed. And so that thing is almost certainly going to return pending. And we can see that we're asking a little helper method here. Is that pending? So the very first time we call it, the answer is almost certainly going to be yes, it's pending. So if sleep is pending, then foo poll is going to return pending. If the sleep's not done, then foo's not done. That makes sense. And if the sleep is done, so okay, so I guess poll's going to get called more than once. We can kind of see that implied in the code here. So somehow poll will get called again in the future. And it may find that the sleep is done. And of course, the second time it gets called, we have arranged for it to not print the start message more than once. That's good. That would be a bug. But then eventually it's going to get called again, maybe many times, and it's going to see that the sleep future is ready, is finished, because the time has passed. And then we go into this branch. And once the sleep future is finished, we're done. We print the end message, and we return the value that says we're done. And one more detail that I'll highlight here before I take questions. We did carefully protect ourselves from doing the first print more than once, because poll's going to get called more than once. We have not bothered to protect ourselves from doing the second print more than once, and we don't have to, because there's a rule, which is that once you return ready, from you being a future, once the future returns ready, it should not be polled again. That's the rule. It's kind of like an iterator. You may know the iterator traits contract is that once you've returned none from your iterator, that means I'm done. And someone could call you again, but they're like really not supposed to, and you're allowed to kind of do whatever you want if they do that. It's a logic error. Same story here. So when a future returns ready, it can just assume it's not going to be polled again. And if that happens, well, it's okay if that's a bug. I saw very skeptical looks, and I see some hands. Was that a question? The skeptical look? Hand.
So I'm assuming that the actual timing work is being done by this sleep future, like counting out the second. And is this line 21, 22, when we make that call, does that sort of activate the timer within the sleep future? So once we make that line of code, then it starts counting the second out, but not before that, like the first time we call it.
Right. So the question was, under the assumption that the sleep future is the thing that's actually keeping track of time, does the poll function like activate its clock in some sense? The answer to that is in part, I don't know. And I just found out that I'm going to get myself in trouble by assuming exactly how sleep futures work in Tokyo. There are a couple different ways it could work. I don't know off the top of my head which one Tokyo does. We are going to rewrite the sleep future. I do believe we have time to do that. And so we'll see how we do it. And that might give some intuition. So any questions about what's on the screen? I'm going to run it while I listen to that question. Mean question. Right. So yes, the the question used an important word that not everybody knows probably, which is state machine. So the question is, if we observe that this foo struct is a state machine and that started is sort of its state, and that means that there are two states, like what does it look like when foo is a more complicated function? Tell me, give me a shake if I'm misrepresenting your question, but we can see back up here in the async function foo, there was, what you were getting at is a really nice trick you can do, which is you can say like, okay, how many awaits are there in this async function? And you have to watch out for loops and conditions and things, but you can say how many awaits are there? And the number of awaits, I want to say +1, tells you kind of the number of states you have to remember. So you can think like the poll function has to keep track of whether it's starting here or starting here. Sort of that's why a bool is good enough, because there's only two possible starting points. That's kind of what started tells us in our case. And if this was like a loop or something else, yeah, they get way more complicated. Yeah, I mean, so probably generally, if you just have a bunch of await points, you can imagine that that's an enum and we're matching on it. And I think you probably know that, and it's a good instructive question. But yeah, so you could imagine that instead of a bool, we had an enum with sort of many different variants that each give kind of a name to the different await points. That's a little tricky when there's a loop or conditions, and I think the only way to give a really good answer to that is to look at more complicated examples and translate them, which I'm not going to do. Yes, writing these state machines by hand can be quite annoying. It's very nice the compiler does this for us. Yes.
Trivia, but if we constructed a foo future and then we didn't wait for it for a second, and then we tried to wait, would we get it to wait for another second, or would the pre-construction of the sleep future cause it to immediately return?
Yes. Right. The question is, for example, suppose we did the bad sleep before we did the await on the foo. Would that then wait for 1 second more, or would it like be done immediately? Right. Something caused us to not poll foo for a while, right? And that does depend on whether like the clock starts when the future is constructed or when it's polled the first time. I suspect it starts when it's constructed. Our implementation that we're going to get to, I'm confident we'll have time, will start when it's constructed. We'll just read the clock when it's constructed. So in our case, if you just didn't poll us for a while, we'll see that the next poll would return immediately ready. Yeah, let's look at it here. In the poll. Yes, right. The question is this a busy loop? And the answer is, it will be the first time we try to write it. And then we'll try to fix that. So no, in like when this is working and it's Tokyo and everything's nice, this is not a busy loop. And what we'll find is that there are entities in the background that conspire to call poll at the right time, which is fascinating. And we will write some of that code ourselves. But it would not be logically wrong for the world to call poll in a busy loop. We should assume that our code needs to be correct in that case. And in this case, it is, right? So it would know that it doesn't return ready until the sleep is done. And if you call it 1,000,000 times, that logic is still correct. That makes sense. Brad.
Yeah, you talked about two contracts that are in the Rust community, like where you shouldn't be polling iterators after they're done. You shouldn't be calling your futures after they're ready.
Mm-hmm.
There's actually a third contract that says your futures will do nothing until you poll them, which makes them lazy. And so that's actually quite distinct from how they're often implemented in other languages. But that is a unique contract that you will see repeated over and over and over again. It is clearly possible to write an eager future, but that is very much against the promise of no work is done until you poll it.
Yeah, that's sort of, I think you were on mic, so I don't need to repeat any of that. But it is an interesting question. So if we had put the first print up in here, if we decided to do it here when the foo future was constructed instead of when it was polled, would that be wrong in any formal sense? I'm not entirely sure, but it's definitely not what async functions do. And I think the problem that a lot of beginners or maybe even experienced Rust programmers, but who are new to async, a lot of the problem we often run into is imagining that the first few lines of the future might execute immediately before polling, and that's not the case. The way that async functions get compiled looks like this, where even the very first line of code goes in the poll. Yeah. So that is, I'll go back to the playground and I'll zoom out a little bit. And I know we can't read it, but I think I just like kind of spiritually kind of seeing all the code in front of me. Like that is a complete replacement of async function foo, the 3-line correct async function foo. So this is what it looks like as a future. So that's what futures are. Okay. So fine, I guess. yeah, I'm done. Let's do something that sounds a lot harder. So foo, I suppose, is one of the easier things you could possibly have. I guess you could have a feature that's never pending. That would be even easier. But foo is a quite simple async function. We might imagine that join all is like dramatically more magical. Like just, are we going to have to is it going to take an hour just to explain what join all is doing? What we're going to find, surprisingly to me, is that join all is no more complicated than foo. That's weird. And I want to look at that right now. See if I'm in the right place in my article. I'm zooming in too far. Yeah. Okay. So this time, yeah, let's look at it in this format. Well, this doesn't behave too well when I zoom in on it. Let's look at it on the playground. And I'll do more zooming in and out with apologies. So this time, this is way too small. I know, it's way too small. I've put foo back. Foo is now what it used to be, async function foo. And now we have written our own join all. And just like foo, we can see that it's returning some struct, which is going to implement future, which we have written. And I'll zoom in real quick to just observe that the only difference in main is that instead of, I think previously we were calling it future : join all, it was coming from a crate called the futures crate, which is some helper functions. Instead of using that, we are now using our join all. That's the only difference. But otherwise, async function main doesn't see anything different. Okay. What does constructing join all look like? Let's look at the struct first. What does the struct look like? Oh, at least it's short. We've agreed not to look at pin. I'm not going to think about it. And box is not doing much, right? Yeah, we box things sometimes. It's fine. So F is like the futures that we're joining, I guess. That is the future type that we're joining. Okay. And what have we done? We just put them in a vec. Just a vec of futures. Okay. And so if I go back down to the function, we will see, yeah, okay. So join all takes a vec of futures. Is that what we passed in down here? Yeah, it is, right? So we created this vec of futures in main. We pushed all the foo futures into them, and that's what we've passed to join all. So join all takes that vec, and it does transform it. So we transform it into an owning iterator, and we map that over box pin. So this creates a pin box of all the Fs, but we've agreed to believe that that doesn't do anything. And then we collect it into another vec. So all we've done is we've boxed all the Fs, but still a vec. It's just a vec of Fs. So all of the magic is in the poll function. Guess that's not too surprising. That's what it was last time too. Let's look at poll. It's actually shorter. It's kind of weird. It's even shorter than foo. So how far do I have to go to the right? Sorry, I do have to scroll to the right a little bit, don't I? I'll zoom out one tick. So essentially all of the heavy lifting is done by this function, which probably most people in the room have not seen. Retain mute. It turns out that retain mute is a stock standard helper method on vec. So sometimes you have a vec full of a bunch of things, and you want to keep some of them, and you pass a closure into the retain mute function that returns true for the ones you want to keep. And then vec does this cute little pointer walking thing so that it only has to iterate once over itself instead of doing the quadratic. It doesn't matter, whatever. If your whiteboard interview solutions happen inside of retain mute. And then our Boolean returning function is, I'm being a little clever here. So in addition to returning a Boolean, I'm doing something. So is pending, what does that do? It takes a reference to one of the elements of the vec. It pulls it, passing in the context again. We're not looking yet at what context is. And it asks, so that poll does work. So I have polled the future, and we know that those futures are going to be foo. So that might print, that might be asking the sleep what it's doing. It might do the final print, right? So it's polling each of those futures, and it's asking whether the return value was ready or pending. So if the return value was pending, this closure returns true. And retain mute is going to call that closure on all the Fs, all the foos in the vec, and it's going to keep the ones that were pending. So when we poll join all, it polls all the futures in the vec. It keeps the ones that were pending, and then join all is ready when all the futures have at some point returned pending and been deleted from the vec. So we'll notice that we're following the rule I said we had to follow before, right? We're not supposed to call poll on a future that has previously returned ready. And we're following that. So as soon as it returns ready, that closure returns false, and it gets deleted from the vec. We're not going to call poll on it again. Good. That's it. Is that really it? I'm going to run this. Yeah, that's it. Kind of funny. So the most magical thing in the world that our program is doing is just a loop. It's a retain mute. All we're doing is looping over the vector and calling poll on each element. And now we can kind of start to see like, oh yeah, okay, I remember when we put the bad sleep in there and that ruined our parallelism and that took 10 seconds. Well, yeah, I guess if each of those polls in retain mute takes a second, yeah, retain mute's going to take 10 seconds. It's not too hard to see how that happened here on the inside. Okay. To your question from before, we could ask, is this going to do the right thing if it's polled in a busy loop? Yeah, it would. It would. It's going to keep looping over that vector again and again and again and again and again, and it's going to get pending over and over and over and over and over again from everybody. But then eventually it'll get ready and it'll delete them all. It'll return ready and won't get polled again. So we still have this question of when poll gets called from above. Like we don't know that yet, but we know that if it's called, we're going to give the right answer. And every time it's called, we're going to tell all those futures on the inside to do as much work as they can. And they agree. I guess this is sort of the contract of poll, which we haven't explicitly said yet, which is that all those futures had better return quickly, right? So when we made the mistake and poll on the inside was slow, right? Then all these calls that are happening inside the retain mute are slow, and this doesn't work. But if they all do the right thing and they all return quickly, then this works. Any questions about this one, Fiddle?
And you shouldn't call poll. We won't call poll again. Call poll again.
Right.
But is this going to do that?
Right. So the question is, are we following the rule? Yes, I think you were probably reading the code when I said this, which is cool and great, and I'm glad you are. Yeah, we're following the rule because every time one of these inner polls returns ready, is pending will be false, and so retain mute, it deletes it. Yeah, drops it. Mm-hmm. Yeah. So that's join all. Okay, that was surprisingly easy. Huh, funny. So we might be feeling confident. And the only mystery really, I'm not going to look at the Tokyo main macro, but the only other mystery that was on the screen was sleep. And sleep doesn't sound that complicated. It's pretty straightforward what it's doing, right? It's just reading the clock. So we might be going into this one feeling very confident in our ability to re-implement sleep. And what we're going to find is we can get code to compile, but it is not going to work, and it's going to be substantially harder to get it to work. So what have I done here? I have to remind myself. So yeah, let's zoom in on the playground version. So now I've put foo back. Foo is still back to async foo, and we've gone back to using the standard join all, okay? And now the sleep inside of foo, that's going to be our custom sleep. So we've seen this trick before. Okay, so what is sleep? It's a struct. What does it contain? A time. That makes sense. So we can probably guess, if I scroll back down here, what does the constructor do? I read the clock, I add whatever sleep duration you've asked me to add, and I store the time when I should wake up. So we had some questions before about whether that was happening during the construction or during the poll. In this case, I do it during construction. Of course, this returns quickly. So there's no like blocking work here. I'm just reading the clock. But that I decide when I'm going to wake up as soon as the sleep future is constructed. Okay, that's not very complicated. And this poll method is super short. This might be what we hoped we would be able to write. So, are we ready? I don't know. What time is it, right? That's the answer to whether we're ready or not. So we just look at the clock and we compare that to the wake time, and this compiles and works it compiles. But it don't work. So what we're going to see is that the futures start. I have a hint. I put a little extra print in there, but so something's wrong. Does anybody know what's wrong? I've been talking a lot. It's fun to have other people talk. I see a hand.
I don't know. Like, my intuition said that this poll shouldn't get called after it's called, where it's called the first time, and it's not going to be called again, right?
Right.
So I think the first time it gets called, it's presumably not going to be ready because time hasn't lapsed. And then it's not going to get called again as per our contract. And so instead of, there has to be some kind of signaling mechanism where it goes out and tells us that it's ready as opposed to waiting for it to be called.
That's precisely right. I'll summarize that to say that the correct guess here is that what we're missing has to do with the question before about the busy loop. We know we don't want poll to get called a gajillion times every second. So somehow someone is arranging to not do that. And it turns out that when we get all the way down to sleep, we are that someone and we haven't done it. That's what's happened here. So there's a third job of the poll function. What were the jobs before? We said it has to say whether it's done or not. That's returning pending or ready. It has to do the actual work on the inside, as much work as it can do without blocking, so to follow the rule that it must return quickly, but it has to do as much work as it can. So it has the return value, it has to do some work, and then the third thing is it has to register a wake up. What does that mean? Right. So it has to arrange to be awoken, awakened, whatever. That word is so funny. And we're not doing that. And what we see is that when we don't arrange for a wake up, we don't get polled again ever. Sucks. So how do we do that? And the answer has to do with this context that we have not yet been talking about. It turns out that context only has one method, which is called waker. And that gives us a thing called a waker. And waker has one method that's kind of two methods that's kind of one. It's called wake. It's got two versions of that method. We see one of them is called wake by ref. I'll pull that up. So a waker is opaque. And we see this is too small for folks to read, but we can see that it's got the wake method and the wake by ref method. Okay. So the provided magical way for us to say that we're ready is to call one of those two methods. The reason there's two is a small efficiency thing that we don't really care about. We'll just call whichever one's convenient. In this case, waker is returning a reference, so I'll call the one that takes a reference. So if I call this, again, I'm inside the future implementation of sleep. This is the poll method, and this is the branch where I'm not ready. So if I say, I can satisfy rule number 3. I can do my third job. This is logically valid, if not a good idea. I can just say every time I'm gonna say I'm not ready, every time I'm pending, I can just say and pull me again, now. This works. So I have changed nothing else, I believe, in this example. Nothing else has changed. I've added only that one line. And this now should work. But we can guess what the problem is. It does work. This is a busy loop. I'm a little short on time, so I'm not going to pop it up in my terminal and run it under one of the commands that lets us see that the CPU is burning. The CPU is burning. That's bad. We can actually, one way we can see that is I'll put a little DBG in here. So if we put a print there, I may be abusing the resources of the playground slightly, and I apologize to the Rust community at large for my crimes. So that's bad, right? So we got to think. Okay, so we have the ability to ask for a wake up. That's cool. But we are the pole function of sleep, and we're not like what we might like to do is just call the standard sleep for a second, then wake up and then say pull me again. But of course, if we do that, we're breaking the rule, right? Because then we're not returning pending quickly, and we know that that ruins the overall performance of our program. So what can we do? And there is a kind of cheaty option here, which is like we could spawn a thread that's going to call the standard sleep function and sleep for a second for real. And then when it has finished sleeping, it will call waker.wake. It turns out that wakers are clone. You can do that. Of course, if we spawn a thread for every foo, or I should say every sleep, but we know that we're going to have a sleep for every foo. If we spawn a thread for every sleep, then if there were 10,000 foos, we would crash, right? That's the problem we saw at the beginning. We don't want to spawn one for every sleep. It is possible to have one thread running in the background and like somehow communicate with it over a channel and ask it to sleep for you and write some clever code that sleeps for the smallest amount of time, and then have that thread call wake. You can do that, but that feels like so bad because like, why are you spawning a thread just to sleep, right? We already have a thread that's sleeping. It's the main thread, right? We're like, we are sleeping. And we like, how do we tell the main thread to wake up, you know, in 0.999 seconds or whatever, right? Like, shouldn't there be a way to do that? And the answer is in Tokyo, there's a way to do that. That's what the sleep future is. But if we're trying to write our own sleep future, we now need a way, if we don't want to spawn a whole other thread just to make this work, we need a way to communicate to the main loop and tell it how long to sleep for. And in our case, that means we actually need to write the main loop. Like, we cannot write our own sleep without either spawning off a thread just for sleeping or owning the entire main function of our program. And I'm now out of time, but I will at least put it on the screen. So in this version, let's see, this is the busy loop version. I'll fast forward. Let's just go to the end. Yeah, we could talk about pin. Yeah, if we have infinity time. So the final working version of this program, when you poll it, it pushes wake times into a global vector of wake times. And then in the main loop, after polling the joined future, it pulls the next wake time out of a global vector, does the regular thread sleep for that amount of time. And then when it is done, wakes up and clears those wakers from the global. Like, that's the way to do this. And obviously we don't have time to go line by line. We're now out of time. But you all have the link. It's in Discord. If you have questions about this, I would love to talk more outside or over pizza. That is what futures look like on the inside. Hopefully that helps to build up a little bit of intuition about what the hell is going on here. And I'm looking forward to writing the rest of this article. Thanks, everyone.
Okay.
Oh, okay. So we have no time tonight, but we also had one person that was ready to speak. Apurv, do I have that pronunciation right? Yeah. Okay. So what we'll do is we'll probably set you up to speak at the next meeting, if you'll be around. And we've got a couple of other talks already, I think, for that as well. But thank you for being willing to speak tonight on standby. And thank you, everyone. Very much appreciate you guys coming out. Please join on the Discord if you have any feedback for me and how we could make this more useful meeting for you. Please let me know, and I'm happy to do that. Thanks again.